We can do this very easily. I do this at high schools. You can go and buy whey protein at the health food store or the bodybuilding store, and you can mix that with solvents. Solvents being things like ethanol, water, glycerin, and you can turn that into a doughy paste like Play-Doh, and you can form that over a pot, come back the next day, and it's solidified, and you got a pot. So you can actually make these at home if you want. So it's actually very easy. So that's what we'll end up doing, except in our case, we run it through an extruder, and we get our pellets, and then we can injection mold that into pretty much anything we want. Now, we weren't the first people who did this. Henry Ford did this back in the 1950s. And this is a photograph of him with a sledgehammer about to hit a car panel made out of soy protein plastics. Now, I don't have a photograph of what it looks like afterwards, but this is what it looked like before. And we can use things like corn and sorghum and soybean and so on, and we can get some fairly high strengths. For example, with ZEIN, which is a corn-based protein, we add some coconut fibers. We can get strengths as high as 16 megapascals. That's equivalent to like a polyethylene. So we can get some strengths and materials that are fairly good with these protein-based plastics. Now, corn has the advantage that if I were to make a pot out of corn protein, I can pour water in it. In contrast, if I make a pot out of soy protein, and I don't do anything to that soy protein, I pour water in this, I get tofu. It's water soluble, and within about 20 to 30 minutes, it's going to start to dissolubilize, and that's what I get is tofu. Now, we can do some things, and we can add adipic acid and all kinds of other stuff, and we can do stuff to the chemistry to make that water stable. And we've done that, and so we've overcome some of those problems. We can even add it to natural rubbers. And not only can we add it to natural rubbers and have it be a low-cost filler, but actually increase the mechanical properties. So these composites can actually be better than the synthetic resins on themselves. The cost, but the bugaboo in this whole thing is going to be the cost. We have to get the cost where we need them to be. If I make my pots out of soy protein isolate, which is about 90+% protein with a few other ingredients in there, I come up with a cost of about $2.51 a pound to make my plastic. That is not cost competitive with polypropylene. Polypropylene sells well under $1 a pound. However, if instead of using soy protein isolate, I use soy flour, I can get my cost down to about 75 cents a pound. Now I'm in the ballpark where I can be competitive with polyethylene and polypropylene, assuming the fracking industry doesn't drive the price of these materials down any further than where they're at right now. And this is where I'm coming back to why I was talking about these other non-organic feedstocks being cost issue. We've been looking at using these for like other agricultural products other than pots for erosion control, making mattings that you can go out and throw and help control erosion. And we've been doing growth tests on these. We've had growth tests on ZEIN protein, not corn, but ZEIN, because ZEIN's not only water stable, but it also kills plants. You used to be able to, you could go out and buy cornmeal and you'd throw it around on the ground and it would have herbicidal effects. Corn protein has that same effect, more so than soy. And we've made big mats of it, and we've put it out in the environment. We've been doing studies with it. We've got some that are relatively thin that look very similar to the films that you can buy at landscaping facilities and so on. But the work has been mostly on the pots. And I want to talk a little bit about manufacturing, because I know there was a lot of questions about how these pots were made. They were all made with injection molding. And this is actually the first thing that happened. This is where I actually wanted to bring up Matt's name. When we first made these, we made these out of corn. And these plants don't look nearly as happy as they do here. And these were some of the very first pots we made. And so we've went a long ways over the last 5 years of making pots out of corn protein that basically killed the plants to now making them out of composite and blends of materials that enhance plant growth. And Dr. Strader is going to talk more about that in detail. This is the 4-inch pot that we manufactured. And it's a bottomless mold. So what happens is there's no ejector pins. Normally there's ejector pins that pop this thing out of the mold and falls on the floor and you got your product. In this case, this is a 3-part mold. The material gets shot in. This stays stationary. This moves with the mold to some extent. The mold comes apart and it's right here. You can go in and reach and pull it right off the part. Last year we manufactured the 1-gallon pot mold. And you noticed that there wasn't as many 1-gallon pot molds because there's more material, but we shot parts off of this out of polypropylene, and the mold worked fairly well. When we started shooting bioplastic parts off of this, the mold didn't work quite so well. It wouldn't come apart. And in fact, well, this is the 4-inch pot. This mold is quite a bit larger. And when Shunker was down in the molding facility, I got this bad email with this really discouraging photograph of where this is attached to the mold. This is no longer attached, and there's about a golf ball sized piece of steel missing. This thing stuck together so tight that when we went to open that mold with a 120 ton mold, 90 ton mold, I think it was 90 tons of force. And 90 tons of force will do some stuff, and it ripped that mold apart. So I had to get in the car and we went down there. Why did this mold work and this mold didn't? It's bigger. We put it on a bigger machine. Well, the materials are still the same materials, but there's one fundamental design that's quite a bit different. Well, we had the lip on the top, and that was somewhat of a problem. And so when we went down, we brought the mold back to my machine shop, and we put in a ring, what's the word I'm looking for? Stripper ring. And it's got a bunch of springs back here that have really stiff springs. You try to squeeze them, you don't think they're springs. You think it's a solid piece of steel. And so when the mold closes, that gets pushed back, and then when the mold opens, that pushes forward. And that's why these have a little bit of an indentation. This thing pushed with a lot of force, several hundred pounds of force to pop this off that mold to get it off of there. So that it did have that. And actually, we did some remachining on the inside of this to try to get it to work. But the draft is quite a bit less on this. This has a nice big draft. This comes down. This not so much. We followed the mold design of what a 1 gallon mold looks like, and that's how we picked this. But that came back and bit us. And we, because when you're molding this stuff, these materials, there's not a lot of people that have a lot of experience with molding these materials, right? We're formulating them for the very first time. And so, well, we learned a little learning experience on that one. So that's why there's some plastics out there that we would have liked to have had made out of the mold. But we ripped that mold apart twice, and I don't know how many chains we ripped apart. But that's the mold we got right now, and for the next trials we'll be making a whole new mold. So, but we did make a lot of parts, and I think that Dr. Schrader will show a lot more in all these studies he's been doing, and so we've been doing all interesting stuff. But other products we've been working on is what are called lawn darts. I'm not sure how we've coined that term, but these are temporary signs that may go into the field for marking, and we've made them out of either composite, either a solid core or co-extruded core, where we have different formulations. Some of it may be pure PLA in the middle, may have some soy on the outside or protein on the outside. And we've been looking at these. These are actually the old sun chip bag. We were involved in doing some of the welding and sealing of the sun chip bag, and so I got rolls and rolls of that old stuff left over, so I just cut it and inverted it inside. So if you open up that, you'll actually see this says sun chip bag on the inside. These are out in my garden. We put them out there. We also have worked with a company, Insight, who is a environmentally friendly landscaping company, and he's been using some of these to look at using for when he comes out and does chemical treatment. His chemical treatments are pretty benign. He kills grass with, for example, with vinegar and that kind of stuff. I'm not sure how effective it is. When he did it on my yard, it didn't seem to do much. But we got to come up with a solution to these. When you run over the lawnmower, the idea is you run this thing over and it all disappears. Well, that white piece of cardboard doesn't disappear quite so well, and it doesn't look so nice in the yard. So there's some issues to be taken care of there. Some of the latest stuff we're doing is looking at biochar. Biochar has been known to be a good, be able to sequester fertilizer and do a time-release fertilization. The problem with biochar is, if you ever worked with it, a little bit like carbon black. You throw it out and it's just a dust and it's going to go away and disappear. So we make pellets that are soy protein and biochar combined, and we've been doing growth studies to see how well that works. And so that's some of the stuff that we've been doing. So the takeaway from this is that make sure you know what you're doing when you do mold design. But more importantly, not all bioplastics are degradable. Not all petrochemical plastics are non-degradable. There are some that are degradable. And each one of these has its own advantages and limitations. And we have to be aware of those and do this intelligently. And I think that the group that's been doing the research here has done a great job of getting us to this. Thinking about where I was at 5 years ago when this little kid showed up at my desk and said, hey, I want to make pots. We've went a long, long ways. So you guys have done a great job. I'll try to answer any questions you might have.